Group 15 includes nitrogen, phosphorus, arsenic, antimony, and bismuth. As we go down the group, there is a shift from non-metallic to metallic through metalloidic character. Nitrogen and phosphorus are non-metals, arsenic and antimony metalloids, and bismuth is a typical metal. Nitrogen and phosphorus are non-metals, arsenic and antimony are semi-metals or metalloids, whereas bismuth is metallic, although not so strongly. The electronic configuration of elements of group 15 are given in the table. The general valence shell electronic configuration of elements of 15 is ns2np3, where n is equal to 2 to 6. The two electrons in p orbitals are distributed as px1, py1, pz1 in accordance with Hund's rule. Occurrence. Molecular nitrogen comprises 78% by volume of the atmosphere. In the Earth's crust, it occurs as sodium nitrate, NaNO3 and potassium nitrate. It is found in the form of proteins in plants and animals. Phosphorus occurs in minerals of the apatite family, which are the main components of phosphate rock. Phosphorus is an essential constituent of animal and plant matter. It is present in bones as well as in living cells. Phosphoproteins are present in milk and eggs. Arsenic, antimony and bismuth are found mainly as sulfide minerals. Explanation of abnormal behavior. Nitrogen differs from the rest of the members of this group due to its smaller size, high electronegativity, high ionization enthalpy, and non-availability of d orbitals. Nitrogen has unique ability to form p-pi multiple bonds with itself and with other elements having small size and high electronegativity. Heavier elements of this group do not form p-pi bonds as their atomic orbitals are so large and diffuse that they cannot have effective overlapping. Thus, nitrogen exists as diatomic molecule with a triple bond between the two atoms. Consequently, its bond enthalpy is very high. On the contrary, phosphorus, arsenic and antimony form single bonds as P single bond P, AS single bond AS and Sb single bond Sb, while bismuth forms metallic bonds in elemental state. However, the single nitrogen-nitrogen bond is weaker than the single phosphorus-phosphorus bond because of high inter-electronic repulsion of the non-bonding electrons owing to the small bond length. As a result, the catenation tendency is weaker in nitrogen. Another factor which affects the chemistry of nitrogen is the absence of d orbitals in its valence shell. Besides restricting its covalency to 4, nitrogen cannot form d-pi-p-pi bond as the heavier elements can form, for example, R3p double bond O or R3p double bond CH2, where R is an alkyl group. Phosphorus and arsenic can form d-pi-d-pi bond also with transition metals when their compounds like PCH5 whole thrice and AsC6H5 whole thrice act as ligands. Oxidation states and trends in chemical reactivity. The common oxidation states of these elements are -3, +3 and +5. The tendency to exhibit -3 oxidation state decreases down the group due to increase in size and metallic character. In fact, last member of the group, bismuth, hardly forms any compound in -3 oxidation state. The stability of +5 oxidation state decreases down the group. The only well-characterized bismuth 5 compound is bismuth F5. The stability of +5 oxidation state decreases and that of +3 state increases due to inert pair effect down the group. Nitrogen exhibits +1, +2, +4 oxidation states also when it reacts with oxygen. Phosphorus also shows +1 and +4 oxidation states in some of the acids. In the case of nitrogen, all oxidation states from +1 to +4 tend to disproportionate in acid solution. For example, 3HNO2 gives HNO3, H2O and 2NO. Similarly, in case of phosphorus, nearly all intermediate oxidation states disproportionate into +5 and -3 both in alkali and acid. However, +3 oxidation state in case of arsenic, antimony and bismuth become increasingly stable with respect to disproportionation. Nitrogen is restricted to a maximum covalency of 4, since only 4 orbitals are available for bonding. The heavier elements have vacant d orbitals in the outermost shell which can be used for bonding and hence expand their covalence as in PF6-. Trends in chemical reactivity and chemical reactions of group 15 elements. Reactivity towards hydrogen. All the elements of group 15 form hydrides of the type EH3 where E may be nitrogen, phosphorus, arsenic, antimony or bismuth. Some of the properties of these hydrides are shown in table. The hydrides show regular graduation in their properties. The stability of hydrides decreases from NH3 to BiS3, which can be observed from their bond dissociation enthalpy. Consequently, the reducing character of the hydrides increases. Ammonia is only a mild reducing agent while BiS3 is the strongest reducing agent amongst all the hydrides. Basicity also decreases in order. NF3 is greater than PS3, greater than ASS3, greater than SBS3, greater than or equal to BiS3. Reaction of N2 with 3S2 is in equilibrium with 2NS3. Reactivity towards oxygen. All these elements form two types of oxides, E2O3 and E2O5. The oxide in the higher oxidation state of the element is more acidic than that of lower oxidation state. Their acidic character decreases down the group. The oxides of the type E2O3 of nitrogen and phosphorus are purely acidic, that of arsenic and antimony amphoteric, and those of bismuth is predominantly basic. The reactions of group 15 elements with oxygen is given as P4 reacts with 3O2 to give P4O6. White phosphorus burns in air or oxygen with a yellowish flame, forming phosphorus pentoxide. P4 reacts with 5O2 to give P4O10 on heating. 4AS reacts with 3O2 to give AS4O6 on heating. 4SB reacts with 3O2 to give SB4O6 on heating. 2Bi reacts with 3O2 to give 2Bi2O3. Reactivity towards halogens. These elements react to form two series of halides, EX3 and EX5. Nitrogen does not form pentahalide due to non-availability of the d orbitals in its valence shell. Pentahalides are more covalent than trihalides. All the trihalides of these elements except those of nitrogen are stable. In case of nitrogen, only NF3 is known to be stable. Trihalides except BiF3 are predominantly covalent in nature. The reaction of phosphorus with iodine and chlorine is given as P4 reacts with 10Cl2 to give 4PCl5. P4 reacts with 6I2 to give 4PI3. P4 reacts with 6Cl2 to give 4PCl3. Reactivity towards metals. All these elements react with metals to form their binary compounds exhibiting -3 oxidation state, such as Ca3N2, Ca3P2, Na3AS2, Zn3Sb2, and Mg3Bi2. The reaction of phosphorus with metals is given as 6Ca reacts with P4 to give 2Ca3P2. 6Mg reacts with P4 to give 2Mg3P2.